So there are continuous time Markov chains that are time inhomogeneous, and this is pretty useful in a lot of different applications. The best way to understand it is to revisit the Poisson process, which we do know has the time homogeneity property. Let's review these calculations very quickly. We've seen these before. So if we're looking at a Poisson process as it's transitioning from a state x, this is going to be an integer x, to some larger integer y, and it's doing so in the time interval from s to t, then we know that the time homogeneity property says that this distribution, this probability, is going to depend only on the elapsed time. The elapsed time here is, of course, the length of the time interval, which is t minus s. So you pick up this t minus s here. And of course, you can also write this in terms of the conventional starting point of the Poisson process. So the Poisson process additionally has this feature that it's always increasing, which leads to just the simple fact that if you count from x to y, that would be the same thing as starting with 0 count in the beginning and counting up to y minus x. So these are one and the same. We've seen this before, and we've seen that this is defined by the Poisson distribution, hence the name Poisson process. And now finally we kind of arrive at the fact that if we view the Poisson process as a continuous time Markov chain, it's going to have these transition probabilities, namely from state x to state y, we're going to transition in some allotted time t minus s, that's the allotted time for this time interval. We're going to transition according to the Poisson distribution. So this is all fairly straightforward. If we now look at a particular example, let's say we take an example where y is equal to x, so this transition probability, this corresponds to staying in a particular state x, meaning not counting up, not moving up at all, during the time interval s to t. So we have t minus s units of time. We want to make sure that we don't count any additional events, which is basically saying that ns is equal to nt. How do we compute this? Well, this just means that the waiting time in state x better exceed the length of the interval. So t minus s is the length of the interval. The waiting time in that state better exceed that, and that immediately gives us this this probability here. So this mu here is kind of static. It's a rate, but it didn't depend on which interval of time was considered. So s to t could have started at 0, it could have started at s. That time interval, as long as its length is the same, this probability will be the same. And that's the homogeneity property of the Poisson process, which we'd like to relax a little bit. So for many applications, the start of the start of that interval, the s in part of this interval, should matter, right? There's a difference between whether we start something when it's night or day. Summer and winter, they're different seasons, so perhaps starting in the summer, the behavior should be different than starting in the winter. And for this reason, in the context of a Poisson process, what we do is we assign a rate that changes over time. So now, instead of mu being a constant rate, just some number, we're going to treat it as a function. So it's going to be a function of time, and at any point in time, let's say we have a time u, mu u is going to be interpreted as the rate at that particular time. So what we're going to do now is take this probability above and write it down in terms of this instantaneous changing rate. And here's one proposal for how one could accomplish this. So we want to start in a state x. We have a count of x, and we want to write down the probability of that not changing by the end of the interval, which is time t. So in other words, we want the probability that nt is equal to ns, given that we started with some count x. And what we're going to do is we're going to tweak this earlier formula to, instead of having a constant rate, we're going to integrate the instantaneous rate over the entire length of the period. And you can see how this formula immediately reduces to the original one when mu is constant. If you want to integrate a constant over time interval s to t, you'll get mu times t minus s, which reduces us to this case. But here you can see that there's quite a bit more generality, and now what we've basically replaced a constant rate with is this notion of a cumulative rate. The probability here still looks kind of exponential, but now it depends on the endpoints of the interval. That's the most important part. So not just the length of the interval matters, not just t minus s, but it's the particular start of the interval, the s itself, that really governs this probability. And it doesn't, there's no way to rewrite this to start at 0 and end up at t minus s, which is what we were able to do in the calculations for the regular Poisson process. So now, the way we're going to think about this inhomogeneous Poisson process is it's still going to be counting events, right? The state space is still going to be the natural numbers. It's still going to have transitions that are kind of incrementing the process at any point in time. So it's always going to go up by 1. But now it jumps. The probabilities of how long we wait in each state and how quickly we jump out of it is going to be governed by this cumulative rate. So this function mu is non-negative. I specified that in the previous slide. Let's see if I did. Yep, I did. So this is a non-negative function, which a rate should be, and this is now a cumulative rate. So it is an increasing function over time. We're integrating, so we're computing the area under the curve. So h is going to be increasing, and as it increases, the larger the rate is, and the more likely the Poisson process is going to jump up to the next state, right, from x to x plus 1. So if we look at this definition again, we can write it in terms of h, or we can write it in terms of the instantaneous rate mu. It doesn't matter, both forms are the same. Right? The difference between ht and hs is precisely this integral, and you can see that the larger this integral is, the more rate we have accumulated, the smaller the probability of staying in a particular state is, which makes a lot of sense. A large cumulative rate is going to have to is basically driving us to leave the state x that we started with. And the converse also holds true. If the cumulative rate is small, right? If the rate that accumulated on the time interval s to t is small, then the probability of staying there at the same count, is substantial, and so on and so forth. So what's interesting here is that the right-hand side doesn't actually depend on x, and for this reason, we can just write down the probability of an increment from time s to time t being 0 as the same probability, right? The x doesn't factor into it. And now it's not too difficult to kind of generalize this. We can take the increment and just say, well, if we want this to be called a Poisson process, right, to have that name, it better be somehow Poisson distributed. And we're going to do this, but we're going to use the cumulative rate in the definition. So whereas before this integral was equal to mu times t minus s, we're now going to keep it intact as the integral. So it's going to be a Poisson distribution determined by the cumulative rate. And this cumulative rate is clearly going to depend on the precise times, the s and the t. There's no way to reset this thing to be 0, right? It's not just the length of the increment that matters, it's how much rate was accumulated over a given time interval from s to t that matters. So here's sort of the final definition. An inhomogeneous Poisson process with a rate function mu, so now mu is a function, is going to have these transition probabilities. We immediately see that we need s and t both there. We need the start point and the end point of the interval, not just how much time passes in that interval. And now the transition probability from x to y is going to have this Poisson-like distribution that depends on the cumulative rate. And as soon as mu becomes constant, then the cumulative rate just becomes mu times t minus s, and you recover the homogeneous Poisson process. And this generalizes further, right? You want to have a time-inhomogeneous Markov chain. It's still better have the Markov property. Here it is. So conditioning on the past, given the present is at the state x, then only the present matters. So the history is forgotten. And the transition probabilities now, again, don't only depend on how much time has elapsed, but on the particular starting and end point. The S and T matter. So this is a transition probability of moving from state X at time S to state Y at time T. And of course, the paths of the homogeneous Poisson process are step functions. The paths of the inhomogeneous continuous time Markov chain are step functions. And they look exactly like the picture below me, so that picture doesn't change at all. The only thing that's different is that now the waiting times are going to have a slightly different distribution. So let's discuss this. Here's where kind of the summary of what a continuous time Markov chain that's inhomogeneous entails. So you still have two ingredients, a state space and these rates, but now you can see that the rates are actually functions. So every single state is going to keep a function of time, and at every single point in time is going to say this is the rate at that time. But that rate could potentially change. That's exactly what's making it inhomogeneous. It's exactly what's saying that these transition probabilities need to keep a track of the starting and end point of the interval, not just the how much time has elapsed bit. The second component, which we had before, doesn't actually change. Like the embedded chain, which tells you where to go from one state to another, that ingredient is exactly the same. The one little kind of caveat there is with the self-transition, and it's sort of obvious what to do. As soon as the rate as a function has any positive value, then we cannot have any self-loops because there's a way to transition out. But as soon as if the rate function is zero everywhere, then we have to add a self-transition there because once the rate goes zero, we stay at that state forever. And this is the final kind of detail, which concerns the waiting times. So the inhomogeneous CTMC is going to look like the picture below me, with the slight exception that the waiting times, the sizes of those steps, they're going to have kind of a quasi-exponential distribution. So if at time tk, which is the kth jump time, we are in some state x, and you want to figure out the distribution of the waiting time in this state, which is tau kx, the probability that we stay longer than time t is going to have this quasi-exponential flavor to it. It's going to be the cumulative rate of that particular state, right? Rx is the rate of that particular state, and however much rate has accumulated, that governs the probability that we stay there up to time t. So that summarizes kind of this bit about inhomogeneous continuous time Markov chains. Certainly important for applications, and it's not too much too far a stretch from the original homogeneous models. Right, as soon as you take this R, Rx or Rz, the rate of the state, and you make it constant, all of a sudden the continuous time Markov chain becomes time homogeneous. So we're going to look at how to simulate these things next, but for now this ends this clip.